The broadcast is now starting. All attendees are in listen-only mode.
Morning, everyone. Welcome to the final session for SimSolid. If somebody could be nice enough to let me know whether you can hear me and the screen. Thank you. So we're just going to give a couple of guys to join, a minute or two to join. Okay, let's begin. So again, welcome to the final session. Hopefully this session won't take us 30 minutes. It's an opportunity for you to ask me questions. So I've got the final present demonstration to go through, in my opinion, a pretty large example, just to sort of finish off the sessions which we have been doing. So the plan is, so we're just going to go straight into SimSolid, just to give you the workflows involved in analyzing something pretty complex in my sort of opinion, which is possibly almost impossible to do inside Inventor stress analysis or even Inventor Nastran. So currently, I'm just going to, for the new delegates who have joined us this morning, I'm simply going to go through this example pretty quickly. So this is something which we had done in the welded seminar or webinar, where we were basically looking at fabricated examples. So typically, I've seen many customers using fabrications or thin structures and still meshing it using solid. So if that's the case, then we will get contacts between two solid plates. So the contact is going to be highlighted by this sort of a black line. So we're not going to get contacts on the edges. It's primarily going to be automatically created between the plates. Whereas in the real lives, when we're doing welded structures, it's primarily that contact remains free and we have contacts on either side of the plates, or maybe even one side plates. Now, if you were to sort of idealize that using shells, then the problem becomes a little bit more difficult, because you end up having gaps between the plates, and then there's no way for us to sort of put welds on there. So we'll have a contact between the bottom of this vertical plate and between one of the edges or the face of the horizontal plate. Or you could create a surface model, which is probably the least popular option among users, where you can basically start creating welds if you want to, using shells or surfaces. If they are primarily structures with uniform cross sections, then you can do beam elements. So obviously you have to think which way you want to proceed, especially when you have thin structures. Now, for the bolted connections, which we went through last week, we have to suppress the bolts, and we can go through and create bolted connections inside a Nastran. And obviously, that is also can be pretty tedious. Now, this was the example which we demonstrated last week, where we have 4 bolts, but if you have almost over 100 bolts, then it becomes a very tedious, and you get to a stage where you make the decision whether to include the bolts or not, and assume in this example here, the red and the green plate will be automatically bonded. And if you want to analyze the bolts, then you can do a localized study, a bit like what we did last week. So I don't want to spend too much time on this. If you missed the last session, I suggest you have a look at the webinar. So in essence, I just want to go through straight into SimSolid and show you now here we have a weld geometry. Now here we don't have welds. So basically what happens is SimSolid, in this example which we did on a frame 2 weeks ago, it will create edge to face contacts. So this box section here, you can see it will create an edge contact to simulate the weld. Now it is not simulating the actual weld size, it is simply calculating or contacting the edge of this box section all the way around onto the face of the frame, and that's how it works. Now you can also, just before I go back, you can also include welds. If you had a weld geometry there as a separate geometry, then you could actually use that in SimSolid to represent the physical geometry as a weld if you desire to do so. Okay, so again, both the connections, we can define these automatically. So I'm not going to spend too great a time going through this example. I would suggest you look at the last week's webinar to see how the bolted connections are created. I will go through it inside this example here. So I just want to go straight in the SimSolid and let's show you what we have. So this is an example courtesy of Pilkington's. It's still not the whole complete frame. And if I was to just zoom in to, let's say, this area here, you can see we have the horizontal frames are basically bolted to the vertical frames using plates and bolted connections. We've got them across all the three vertical beams. And also we have numerous amounts of plates. If I zoom in here, you can see straight away that there are plates with no weldments. So the plan in this example here is to basically have a combined welded assembly with bolted connections on a pretty detailed model. So let's just be simply, so I've got the model here. The first thing I'm going to do here is just, first of all, let's assign the materials as the step file. Okay. So once the material has been assigned, right, what happens normally, as you can see in the previous webinars, is that when we bring in the step files, it wants to automatically create connections. This is sort of little symbol you get. Now, typically, we don't want to do that. The typical step in the workflows is that you want to create the welded connections first. Once you create the welded connections, then we will create the bolted connections. So what we're going to do here is, so I'm going to just cancel that. Now, basically, the horizontal sections or the frames are all welded. So what we're going to do here is we're going to isolate everything else and then create welds between this structure and this structure here. And there's numerous ways we can do this. So we can go into here. And so there's my sub-assemblies. So the ones I'm going to pick, the horizontal, so the vertical ones. And let's hide the selected parts. So I have got the bolted connections, but it's not going to weld the bolted connections and the holes because we're going to set a tolerance for my welds for a minimum size. So let's zoom out again. Okay, so in the connections, I have various options. We're going to create a seam weld, and there's numerous ways we can actually create the welds. So let me just zoom that out. Now you can see here you can create a weld from a solid geometry. So if you're using weldments or create a fillet or a chamfer around a box section, you can take a geometry and create that or represent that as an actual physical weld. But in my case here, or in this example, I'm simply going to group, first of all, minimum length. We basically are going to ignore any edges below 50 millimeters. The section size is not the physical size of the weld, as per mentioned 2 weeks ago. Well, not 2 weeks ago in session 4 or webinar 4. It's basically a tolerance. It will pick up any edge which is in contact with a face and will create a weld between an edge and a face. So just remember that it's not the physical weld size. So I'm going to pick group welds. If I just let's do a window selection. Okay, so here I have selected all the components. Now, because the two sub-assemblies are not connected, it's going to weld this sub-assembly and weld this sub-assembly. So if I find the welds, this is a bit like having automatic contacts inside, let's say, Nastran, but the beauty here is that it's a solid plate and it's going to create contacts on either side of the plates. Okay. and which is a pretty tedious task inside Inventor Stress or even Nastran, because what will happen is if I zoom into an area, let's take this example here. Can you see what happens? It basically creates an edge of that vertical plate and creates a contact between the horizontal beam. Inside Nastran, for example, what would have happened is would have created a face contact of that plate with the face contact of the horizontal beam, which is not strictly speaking correct, but obviously that's how it works, and it's, I think, a pretty big task to suppress all them and then go and reconnect the edge with the faces of the beams. But here it's done correctly, so I'm happy with that. You can change the tolerances. You can have intermittent welds, so you can basically specify welds, sizes and lengths along a beam. So I'm happy with that, so I'm just going to press OK. So I've created some welds. And now what we're going to do here is I'm simply going to bring back the vertical sections, okay, and weld these vertical columns. So I'm going to pick these. So let's pick that one. And then I'm going to hide everything which I have not picked. So you can see here all the welds are there. So I'm simply going to pick all these now using the same command we did. Okay, that need to be in connections. So go into welds. Again, group size, group welds, draw a window around all that. So now it will create welds between these. So let's find welds. So think of it as like creating contacts. So it's done that. It's created 232 contacts in total among the 3 vertical sections. Okay. Now, once we have created all the welds, let me show you. So if I'm just going to zoom in here. You see there's the welds created, and now obviously I don't want to create a weld between this plate here and that face of the column because they are connected with the bolts. So what we're going to do here is we're simply now going to go into bolted connections. Now, because I have created these welded contacts or welded or welds, in other words, we do not want to create contact, between the welded sections. So I'm simply going to go in here and ignore all the plates which have got a welded contact, and it's going to ignore all that, and it's going to create contacts between everything else. We're simply going to press OK now. And it's primarily going to create contacts between this plate and that section and all the bolted connections. Now it is going to create hundreds and hundreds of contacts. So what we'll do here is let's just pick one of these bolts, for example, and let's review part connections. You can see here, based on our analysis or webinar last week, it creates contacts automatically. The red bits represent bonded contacts, and the yellow ones represent sliding. So the bolt, it's got a sliding contact between the plates, for example. So it creates that automatically. So now we've got the contacts created and the fasteners. I'm going to go and create the stress analysis. So let's just go and create a static linear analysis. So in this example here, I'm going to create a couple of studies, and we're going to what's happened here is that everything is bonded. So we're going to run as a bonded analysis, then we'll change the contacts between these plates because in reality they'll be separating or sliding, and you can then basically compare the results. So let's just first of all do the easy task of grounding the columns. So pick that one. So these are fixed to the ground, and we're simply going to apply a simplistic load. It's a gravity load, and we'll get a stress due to its own weight of the frame. And the gravity is defined by a vector automatically, so that's going to be in the -z direction. Okay, and I think we can check if everything's okay. Now that's checking for any rigid body motions, and that's a pretty good check to check if any of the constraints or contacts are missing. Now, because it's a pretty big model, it'll probably take, I hope, not too long. I could have run the simulation and assumed everything was fine. Okay, there we go. So we're good to go. So just be aware, everything's bonded. So I'm just going to run this just to give you an idea. Now, obviously, in the previous webinars, if I just expand that here, is adapt for stiffness here. Obviously, this takes, if you're interested in displacements or you want to get a feel for that, if everything looks okay, then that is the first run. It goes through 3 passes. Now, if you want to look at detailed stresses in the structure, then I would suggest we run it as adapt for stress. Now, that will probably take about 7 minutes to run live. So I'm not going to go and use that example. I'm simply going to use adapt for stiffness here. And let's just run that. And this would probably take a minute or 2 now. If we were to do this something similar inside Nastran, perhaps as a shell model, I think it's probably going to take you more than a couple of minutes. And if it was solids, then that will take you a good half an hour to an hour, even longer. I have when it's with all solid elements. Unless you do it as beam analysis, but beam analysis is very quick, but then again, you don't have the ability to do the bolted connections, because with beam analysis, we have to assume that everything is connected. And what typically happens in the FEA world or structural world is that they'll do a beam analysis of this frame you see on the screen, and then they do a localized study, a bit like what we did last week with bolted connections and fasteners. That's one way of doing it, and that's a valid reason or a valid workflow. But with SimSolid, we don't have to think like that. We're simply working on the native geometry. Okay, in this case, it's a step file, but it's more or less unsimplified. So now it's going to the pass 2. And we were expecting it to run for the pass 3. Now the geometry is not symmetrical. There is a little bit of difference, if you can see on the screen. So I'm not expecting symmetrical displacement results. For example, this is wider than this one here, so we'll probably get more displacement on this section here, but we'll find out in a moment. And this is where the strength of SimSolid comes. It's super fast, and it's actually applicable to very, very large models. And this is a really nice example. Okay, I think we're almost done. With something like this, I wouldn't have actually run the model live using either Inventor or Nastran, because it would have actually taken almost majority of the webinar time. Okay. I think we are good to go. Just updating the display so that, okay, there we go. So if I just look at the displacement results just for a moment, you can see we have more red here. And if I look at my deformed shape, and what I'm going to do here is I'm just going to zoom into this area here. Okay, let's get rid of that one here. And let's have a look. Okay, you can see that plate is connected here. So what I'm going to do here is I'm just going to create a bookmark. And this is one thing I like about it. And I'm going to clone this study now. And what we're going to do here is I'm going to change the contacts. I mean, I'm not going to do all of them. Let's just do this plate here. So if I go to connections, let's pick that plate, and I'm going to do the review part. I'm going to do the review part. I'm going to change the contacts here. Now you can see it's red. Red basically means it's in actual as a bonded contact. I'm simply going to click on this piece here, or the plate. Now I didn't expect that, so okay, and then pick the column as well. Let's see if that gives me any. There we go. Now if I highlight that bonded contact there, I'm going to change that, and you can have sliding without friction or separating. So I'm going to do separating here for a moment. You can specify a friction, and I'm going to close that. Obviously you need to do that for all the other ones. I'm just going to leave it here for this one here. I changed it on the structural one here, so we'll run that one again anyway. I was hoping that I would change it on here on structural 2, but it doesn't really matter, so I'll run that structural one again. Now because I'm using separating contacts, I need to change the contact settings. So let's have a look in here, setup. So I'm going to use separating contacts, and let's run it again. And now what I'm expecting is the plates to open up. Now what I was hoping for is that I was going to change the structural 2 analysis, but it doesn't really matter. But what we can see, you can see the differences. So in something like this, there's about 6 plates. We would pick all the 6 plates and then change the contacts from fixed to separating, and then run the simulation again. Now the separating is a nonlinear contact, and obviously like Nastran, it does take a little while to run. Now because we already run this analysis, the second time run should be a lot quicker. So let's have a quick look at displacements, and you can see here straight away the plate opens up by, actually it doesn't open by that much, it is actually scaled up, but it gives you the feeling that the contact is set correctly. And then we can look at the contact stresses in the bolts and the plates. So I'm not going to go into too much details, but what I wanted to show here is that basically an example like this can be done pretty quickly and pretty easily inside SimSolid compared to our Autodesk solutions, but it's entirely up to yourselves. Obviously there's a lot of things we have to think about and consider before we even start to apply the boundary conditions. There's a lot of work required inside Inventor before we take it into Nastran. So I hope it's given you a quick overview of what can be achieved in large scale examples. And since it's the last session here, I just want to spend a little bit more time on any questions on the trials you may have been doing. So obviously I am guessing that the trials, I've not had any response from anybody yet, but I think the trial season is going to end, or you may have an email from Altair by the end of this month. And obviously these were the supports. Training courses are still happening. I think you still have a week left if you wanted to attend any of the courses. And I think this is an opportunity now to see how you guys have found the trials, any questions you may have. I may be organizing more webinars in August on specific items, or more training or more tips, but obviously it all depends on the feedback I get from the people who have been attending and supporting me in the past 2 months and attending these sessions. So I'll hang around for a couple of questions. I'm also available on my email contact if you want to touch base with me afterwards. So, but I will be getting in touch with everybody to see your experience on SimSolid and get some sort of personal feedbacks and how you may want to apply it in your workplace. So I'll hang around, we'll go quiet for a moment. If any questions anybody has got. Okay, the current version, now what's going to happen, the SimSolid can open Inventor files one release down, so the current version of SimSolid should be able to open 2020. So the one I have got on here will only open 2019, but if you download the latest software, it will open 2020 files, and there will always be 1 year backward compatibility unless you go through the Fusion route, which basically opens the latest version models inside SimSolid. But I don't think it should be a barrier, because we're not simplifying anything, and it's probably easier that if you have a huge assembly, you might as well simply step out a single step file and then work on that rather than hold a complete assembly. But that's my opinion. It would be nice if you had the option, but at the moment the only option is that you can work on the current release of Fusion to transfer geometry SimSolid or one release back inside Inventor. Okay, I have one more question here. Yes, SimSolid is a network license, not a standalone license, so you can actually have it installed on all the users, and first time first serve. So it's basically like our network licenses in Autodesk. Okay, I'd like to thank everybody for supporting me and attending these sessions in the past 2 months. If you have any questions, don't hesitate to contact me, and hopefully I'll be in touch with each one of you in the forthcoming weeks. Thank you very much, guys, for your help and support. Thank you.